most of all, thank you very much for having me. When I got the email last year that whether I could serve as a keynote speaker, 15 years ago, I never imagined that. I just started my career at that time in formal methods, and just, after 15 years, this can go there. I was very humbled, and knowing also that this is the 25th edition of formal methods, so it is a big honor for me. Yeah, so I come from, I'm Hungarian, from Romania. This is one of the countries, actually I looked on a statistic, there was no submission from Hungary, so this is somewhere I think Eastern Europe can improve, and I think it does by actually having quite many of us working abroad. So with that, I will focus on how actually I think some of the strengths from Eastern European education can help in formal methods, and I see that really in terms of computer algebra and computational logic, which is known to be symbolic, or it's considered to be symbolic computation. And I'm going to focus on symbolic computation in the perspective of how it can help automated program reasoning, and thus how can it help formal methods development. So before that, let me just, before getting into technical content, let me just give you a bit of like a pitch why this could be actually useful. And here's a screenshot of one of our own software tool. It's called the Vampire Theory Improver, which is about 250 lines of code, C++ code. Of course, you all believe that Vampire is error-free, and it's working perfectly. It wins competition. It's done well. But it is just a belief, and you want to make your software trusted or trustful. So here, really, the thing where formal methods can help, and especially automated program reasoning can help, because it's unrealistic to expect that humans could analyze such kind of code. So what you would do here, if I would just zoom in the code, you would see every line of this screenshot, it's one C++ code. So human reasoning about such programs, it's very tedious. Actually, it's not even viable. So this is where automated program reasoning can come into. By knowing the boundaries where automated program reasoning can help, actually. So now let's just jump back from the Vampire code. This is the fictive code, which is really not used in Vampire. So assume you have somewhere in your big piece of code, you have this very small program, very like few lines of code, and what essentially is doing, you take an input array A and you partition the array in two other arrays B and C, depending whether your elements are positive or negative. So now what I just said, it's pretty much one of the expected behavior, one of the expected functional behavior of the code. How you formalize that code, how you actually prove that this is the expected behavior of the code, and how you do it, you essentially, since it's a loop, from formal methods, well, you need to reason about, since it's an unbounded loop, you need to reason about arbitrary execution of the program, arbitrary iteration of the loop. And what you have here, you have a program property that exactly does what I just said before. For every position, let's say in the array B, so I quantify over the array elements in the big array B, I know that this array element B is coming from array element A. It can be a scary formula in the sense that what you're doing here, you have first order logic, you have quantifiers, so you universally quantify over array regions. You also existentially quantify over array regions, since counting cannot be expressed in first order logic. So you only know that there is some element from A that was mapped into B, but you don't know which one. And in addition, you have some uninterpreted function A, you have also addition, you have inequalities. So first order logic, it's not enough. You have first order logic with theories whenever you want to reason about program properties. And such program property can be automatically derived if you use automated program reasoning. Now, another aspect is that actually arithmetic can be much more complicated, and this is one of my favorite examples from discrete math. So assume that, so there was this uninterpreted function called h, and just assume that this program, again, a fictive code, the names are quite intuitive. Well, what we are doing here, we are computing the Fibonacci number series. Okay. And while we all know what Fibonacci numbers are, so they are every consecutive, so one Fibonacci number is the sum of the two previous Fibonacci numbers. Unfortunately, 14,000 is not a Fibonacci number, but maybe the 70,000 volume of FM will be. Fibonacci number. Actually, is the Fibonacci number, is this code really, I'm claiming that it's implementing the Fibonacci number, but is it really doing it? And how would you verify it? How you can actually ensure that what you wrote there is actually implementing Fibonacci numbers? So there are various ways to do it. Explore this property that would express some functional behavior or some polynomial relations among Fibonacci numbers. And now, while we all know what Fibonacci numbers are, you might not know that Fibonacci numbers actually satisfy a polynomial equation of degree 4. So you might not come up with this automatically, but again, you can use automated program reasoning or formal methods tools to analyze this very simple piece of code and generate you this invariant, which will tell you that if your program implements a Fibonacci number, you have to satisfy this invariant. So you can use automated program reasoning in various frameworks and in various settings, depending on the logical expressivity that you want to address. So if you want to go for first-order logic with theories, you might go with arrays, uninterpreted functions, arithmetic. If you want to go, let's say, only just with numeric domains, you might need to go with polynomial arithmetic. And all this together is what we are trying to combine in my research group, which is automated program reasoning. So this is why I also chose the title accordingly. And what we do, we combine computer algebra, so supporting polynomial reasoning, symbolic computation, recurrence equations, with first theory improving with the support of loop analysis. And the research is generously funded by the European Research Council, as well as the Austrian Science Funds, WWF, and Amazon Web Services. So now let's just get into the technicalities. How do we do it? So I claim I can do it. I can show you that we can do it. All the things that all the examples, or the small example that I show you, and the output that I showed you is generated through our approach. So what is our recipe to automate program reasoning? And let me just explain you in a very high-level setting first, and then I get into the details how we implement that. So now I'm going to focus on one aspect of automated program reasoning, namely that you are given a loop and you're given an assertion, where prove that the assertion or prove that the loop satisfies the assertion. If not, give a counterexample. Now, since it's a loop, essentially loop reasoning, when it comes with unbounded loop reasoning, requires loop invariants, or properties that hold at arbitrary loop iterations. So our recipe is actually as simple as we can describe it with two colors. So I'm going to use a bit of coloring here to give you the high-level intuition what's happening here. So we are giving a loop, and every symbol in this loop defines the first-order language that we are going to work with. So the symbols of the loop define the first-order language that we are relying our program reasoning upon. All symbols are colored in red, are in black. Now having one color is not nice, so I go for two colors. And how we do it, we start with a loop, take all the symbols from this loop language, and want to reason about these symbols. I want to reason about this loop language. However, when you talk about a loop, you naturally start talking about what's happening at a particular iteration of a loop, or in general, what happens at an arbitrary iteration of the loop. Loop iterations not necessarily be part of your loop language. So what we do, we extend the black language, which is the loop language, with some extra symbols that I colored, well, it's red. And what we do, we try to derive valid loop properties in this extended language by using both colors, both black and both red. Such red symbols or extra symbols would be, for instance, a loop counter. You might have some expectations. If you go with probabilistic programming, you want to reason about expected values of particular variables. If you go with arrays, you might want to reason what happens at a particular update with the array. So we would introduce update predicates. If you go for relational verification, in security, you would compare execution traces of a particular program. So all these things are not part of the original loop language, so we extend the original loop language with some extra symbols. Then we, by some static analysis, which I will come a bit in a moment, we derive loop properties, which are valid properties based on the underlying static analysis that we are applying. Now, these loop properties, you will use both black and red symbols. However, the assertion we want to prove only uses just the black symbols. So what we will do, we take the loop properties and derive consequences while eliminating the red symbols, ensuring that at one point we are deriving a black property which improves the assertion. And these are the workhorses that we are deploying. Okay? So depending on which domain of program reasoning or program analysis we are going to use algebraic recurrences, statistical moments over probabilistic programs, extensionality axioms over array theory, trace lemmas for reasoning about execution traces of particular programs. And these are the techniques that are part of formal methods or symbolic computation for statically analyzing loops. These are the things that help us to derive the loop properties. And then while trying to derive logical consequences of loop properties, we are again using different approaches depending which underlying domain we are working in. So if you use only polynomial algebra, deriving consequences would correspond to variable elimination, which can be done using Grosvenor basis computation. If you go a bit beyond polynomial equalities, if you go to polynomial inequalities, you would do quantified elimination over real closed fields. If you really go to the full first order fragment of first order theories, you can use saturation-based first order theory improvers, and even more you can do, you can actually now automate some inductive step in first order theory improving. And all this together, it's what symbolic computation gives you. So symbolic computation is this algorithmic approach to symbolically analyze objects, and your objects can be your programs. So now for the purpose of this talk, while this is the high-level picture, I'm going to focus only on the upper parts. I'm going to take the algebraic aspect of automated program reasoning and show you how can you use all these techniques to generate assertions or prove validity of loops manipulating numeric valued variables. And the path, this is going to be our journey. It's like a game. We start easy, then you go to a medium level, and then you go to the hard level. So I will start with polynomial loops, and I call those loops solvable loops. So those are the easy cases, but you will see actually the easy cases are not always that easy. Once you have the polynomial solvable loops, we will go one level higher to go to the probabilistic solvable loop. So when you don't really just reason about exact values of a variable, but you need to reason about expectations of variable because you have a probabilistic distribution in your program, like flipping a coin. It'll show you that some of these things are still solvable, meaning they are actually decidable in terms of invariant generation. And then, of course, knowing the general limits of computation, well, we immediately reach unsolvability by very small tricks. And this is the last level I'm going to address. So let me tell you how actually polynomial solvable loops, which I would call them P-solvable, but I just call them solvable loops for the simplicity, can be handled by symbolic computation in terms of generating invariants. Even more, we will generate the strongest inductive invariant of the loop. So I give this very simple program. And let me just focus on some aspects. So what we are going to consider here, we are just considering partial correctness of the loop. So I don't care about termination. So in principle, whenever you give a loop, I will say while true. I don't care of the loop condition. I'm trying to just derive invariants or loop properties that hold at arbitrary loop iteration, no matter what the loop condition is. So if you remember on the high-level picture, now we're in this black language defined by the loop symbols. So everything is black. But it's too little, so we introduce a loop counter, this red variable here, in order to express relation between two consecutive iterations of the loop. But arbitrary two consecutive iterations. So if you do that, the nice thing is that once you're in the programming language domain, you go immediately to the algebraic recurrences or to the mathematical domain. Because what we actually can read off recurrence equations from the loop body. So intuitively what this update statement says. So in logic, it makes no sense that x equals to 2 times x, but in programming languages, it makes a sense, and the sense is that the next iteration of x, the value of x at the next iteration is 2 times the value of x at the current iteration. And this is exactly what I wrote down here. So what we are going to view from now on, program variable become functions of loop iterations. And as such, they become sequence variables, or algebraic sequences. Similarly, you do the same for y, and then you read off that the next iteration of y, so the n is given by 1/2 of the previous iteration of y plus 1. And then from this point onwards, when we do this mapping, so when we do the abstraction from the programming language to the mathematical representation by algebraic recurrences, we don't need to care about program semantics. We actually capture the program semantics by these recurrence equations. And now all we need to do, we need to solve, or we need to reason about these algebraic recurrence equations. Symbolic computation, in particular, combinatorics help us because they are methods from symbolic summations that you can apply here and compute the so-called closed form representations of those sequences. So it's quite easy to see for x. It's a geometric sequence. So what you have, the value of x at arbitrary iteration n is 2 at the power n, so the exponential sequence, multiplied by the initial value of x. So I don't want to go, so if I, for instance, if you ask me what is the fifth value of x in the particular loop, of course you can go to 1, 2, 3, 4, or you just plug this closed form representation and plug n to be 5, and you get immediately the result. Now, this can be done in this particular case, and why it can be done, because you will see that this corresponds to the so-called solvability criteria. But before that, I would just want to emphasize, so you might have thought at the beginning, so this is a very, very simple loop. It is a simple loop. It's actually an affine loop. But affine programs can be actually quite complicated. And you can see how complicated that is. You start from linear arithmetic or linear operations in your program, and the closed form representation of the loop variables actually involve exponential sequences. So you don't have to have very complex programs to have very complicated arithmetic. And Fibonacci numbers are actually an example of that. You have, also in the case of Fibonacci numbers, you have linear arithmetic in your loop, yet Fibonacci numbers satisfy a polynomial relation of degree 4. So while this is great, now if you want to automate program reasoning about such programs, and you start deriving some logical expression at closed form formulas, but it's very hard already for computer programs to reason about linear arithmetic, let alone polynomial arithmetic. But now what you have here, you have even exponentials. So it's even harder in the arithmetic scale. So what we do a kind of abstraction, a sound abstraction, in a sense, try to get rid of the exponential sequences while maintaining the polynomial arithmetic of the loop, or the linear arithmetic of the loop. And for that, what we do, we introduce new red variables, so extra symbols for the exponential sequences that are in the closed form solutions of the loop variables. And I replace these exponential sequences by the respective new variables a and b. And in addition to these exponential sequences, I also compute the polynomial dependency among the exponential sequences. So the abstraction is, it's a polynomial abstraction because I'm computing polynomial dependencies, or so-called algebraic dependencies, among exponential sequences. And why is it useful? It's useful because then I only need to work with the new closed form representation of x and y, which is polynomial in a and b. And I also have this polynomial relation among a and b. I don't have to care about exponential sequences anymore. So I start from a linear loop, or an affine loop, whose arithmetic is given with polynomials with exponential sequences. I do one step back to go to the polynomial domain. And then the nice thing that in the polynomial domain, at least I know how to derive logical consequences. How can I get rid of the red variables? Well, I can get rid of the red variables by applying Grosvenor basis computation over polynomial equations. And how you can read of this equality is essentially, it's a logical consequence of these 3 polynomial equalities on the slide. So I take the three polynomial equalities as an input to Gröbner basis computation, and I compute a logical consequence as a polynomial of these three polynomial equations. Even more, polynomial invariants have a very nice structure. It's the structure of the polynomial invariant ideal. So in linear algebra, it would be a vector space. In the polynomial algebra, you have ideals. Ideals always have a finite representation. So it's an infinite object with a finite representation. So what I compute here, I compute a finite basis of all polynomial invariants. And this finite basis is given by this one polynomial, which means if there is another polynomial invariant for your loop, it should be a logical consequence of this one. So it's quite a strong result. By these steps, what you can do, you do symbolic, so you do abstraction of loop into recurrences, solve recurrences, compute algebraic dependencies among exponential sequences in order to derive the strongest polynomial relation among program variables for that particular loop. This cannot go for arbitrary loops, and here's the catch. It can only go with so-called solvable loops, which means we are imposing some structural constraints on the polynomial assignments and the polynomial arithmetic of the loop, as well with nested, and we can also allow nested conditionals under additional restrictions. And the restrictions are as follows. So we impose the structural constraints on the polynomial updates of the loop such that when you compute here the recurrence equations, then the resulting recurrence equations are so-called linear recurrences with constant coefficients, which is known in the mathematical space as a C-finite recurrence. So that's a very, very strong restriction because you don't allow arbitrary multiplication or arbitrary polynomial arithmetic in your loop. But if it comes with a nice property that if you use C-finite recurrences, then you can always compute closed forms. And actually, that's it, what you can have. There's no other class of linear recurrence or recurrence equations that have these properties. It's a very simple class of property, but it's also the limit of computability in terms of computing closed form solutions. In addition, we also ignore tests. So pretty much what we are given, if you are given us a polynomial, a loop with a multi-part loop, then all tests are ignored, so we are considering non-deterministic programs. But under these restrictions, so we have to make sure that the resulting recurrence equations of the loop are C-finite recurrences and the tests are ignored. Then under these conditions, you can do symbolic summation combined with Gröbner basis computation to compute the strongest polynomial invariant of the particular loop. And all this is implemented based on symbolic summation and polynomial algebra. The approach is implemented in Alligator. So you can go and try it out, and you can use this kind of loop, get this invariant. Now, invariant generalization is just one aspect of what symbolic summation or symbolic computation can give you for loop analysis. You can use very similar techniques for analyzing loop termination. You can do it for program synthesis. You can use this further for deductive verification, namely use the invariant or generate maybe not the strongest invariant, but generate an invariant which is good enough for proving your program correct. So the solvability of the loop comes with these two restrictions. So it's solvable as long as the arithmetic of the loop can be represented by C-finite recurrences. So with that, you have now the overview of level 1. So that's the easy level. And let's take it harder by addressing emerging aspects of programming, namely probabilistic programming. So what happens if you still have solvable loops, but now you actually extend it with some probabilistic distribution? Maybe you have a solvable loop, and in addition, you will start flipping a coin in this particular solvable loop. So will it change? Will it affect the aspect of deriving all possible polynomial invariants or all possible invariants of this loop? And let me just explain what I mean by flipping a coin. So here's a random walk example, a very simple example from probabilistic programming. And how you should now understand this loop is that, so again, it's while true. I don't care of termination. But what is happening this assignment is that I have this additional construct in brackets which tells me the probability. So with probability 1/2 in this case, I'm going to decrement x, and with probability 1/2, I'm going to increment to x. The probability can be any value between 0 and 1. But just for simplicity, I use now half. So now it's not anymore a deterministic action. Okay, so we are updating the value of x depending on a probability. Depending whether you choose to go to decrement, or depending whether you choose to go to increment the value of x. Behavior of a probabilistic loop. It's not exactly as it was before, where I tell you that no matter how many iterations of the loop you take, the exact value of x is a particular value. That was the case for solvable loops. Here, the question is reformulated in terms of, okay, what is actually the expected value? Because there's always a probabilistic choice that you might just always decrement, or you might always increment the value of x. But in average, what is the expectation of the particular loop? And this is actually addressed by expected values or statistical moments of loop variables. And I'm going to use this notation, which is again a red symbol. So I'm going to extend the loop language with these new symbols, which I call E variables, that are just computing the expected values of program variables. And for this particular example, it's relatively easy to see. You start with value x to be 0 initially, and then you do like you flip a coin in the loop. With 1/2 you go left, and with 1/2 you go to the right, depending whether you increment or decrement the loop variable. So the expected value of x is 0, but it doesn't mean that the value of x is going to be 0 at every iteration of the loop. It's just the expected value of it is 0. So while in the previous setting we were really reasoning about exact values of program variables, in the probabilistic setting we are going to reason about expectations. What are the expected values of a program variable? So variables have become like distribution of their values. Now you might think, is it really enough just to think about expected values? So if you ask this someone from applied statistics, it will say, of course not. Expected values are not enough. And here's an example why they are not enough. I'll give you another program, again with the same semantics. With 1/2 you go to the left branch, with 1/2 you go to the right branch. You start with x being equal 0. You do the same thing in either of the two branches of the updates of x. Well, the expected is going to be 0 here as well. So then what does it mean? Does it mean that the two programs compute the same distributions of the values of x? The expectations of expected values of x will tell you, yes, there is. Like, they have the same expectation. But clearly the two programs, even if you just look at them, they are not the same. So if you don't believe, so what we did, we just sampled the programs. And this will be, so we just run the program and just collect the values. For the random walk, this would be kind of like a uniform distribution. So it would be, this is how the sampled values would look like of x. But for the other loop, if you sample or you compute the value of x, it will be a slightly different distribution of the values. So visually speaking, they are not the same, but how do you capture them mathematically? And how we capture them? By going beyond expectations, by going to reason about higher order statistical moments, such as variance and even further. So you want to understand what is the value distribution of the program variables. And if you do the variance, so this variance which is pretty much computing so it can be derived from the second order statistical moments. The expected values of variable correspond to the first order statistical moments. Then you go for the second order statistical moments to give you the variance of the variable, so-called variance of program variables. And then you observe the difference. So you observe this very precisely, and again in a closed form representation. Because in the left-hand side, you have, again, like an exponential sequence for giving you a second order, higher order moment. Whereas on the right-hand side, you just have a linear function. So the two are clearly not the same. And you can capture the difference in the behavior of probabilistic programs if you start reasoning about not just about expected values, but higher order statistical moments, such as variance, third moments, fourth moments, and so on. Now, of course, the question is, well, what can be done? And we recently had this, so we're always interested, what is the limits of solvability, or what is the limits of computability? And for that, solvability in our case would be moment computability. So if you give me a probabilistic loop, can I guarantee that I'm able to compute all higher order moments? From statistics, we know that higher order moments are not always computable, but what about loops? Are there some restrictions of program loops, or probabilistic programming loops, for which higher order moments are always computable? The same question was raised for the level 1 problem. What kind of loops exist for which closed form solutions are always computable? So I want to address the same question, but now closed form solutions for expectations, or for E-variables, or for higher order moments. So I introduced this notion of moment computability, which really stands that the higher order moments of a particular loop are always computable. And the result tells us, this is our moment computability result, and the joint work with Marcel Mosbrugger, Miroslav Stankovic, Ezio Bertocci, that we can really impose, or we can characterize a class of programs for which the higher order moments of those programs are always computable. And surprisingly, it's not very different from level 1. What comes into that, you have to embed the probabilistic distributions. But we can also handle if conditions, as long as the if conditions are always finite, and the polynomial arithmetic, or the arithmetic on the programs, you have non-finite variable dependencies polynomially. So let me just explain what I mean here, and I give you the highlight how this works. So moment computability gives you solvability for probabilistic loops. And these are the main features that we can handle. You can actually work with parameterized distributions, so you don't have to work with constant distributions. You can have symbolic distributions depending on a parameter, which is, for instance, useful for sensitivity analysis, because if you tune the parameter in your probabilistic loop, you can get different values or different expectation of your loop. Now, again, the second item is the crucial thing. So we do allow random polynomial assignments, but we allow it such that we ensure that the residing recurrences over higher order moments will yield you again C-finite recurrences. Now they will be not C-finite recurrences over loop variables, but they will be C-finite recurrences over moments. We can have finite valued multipath conditions, which meaning that the conditions are pretty much a range over a finite domain. So under these three restrictions, moment computability will tell you that higher order moments of solvable probabilistic loops are always computable. And let me tell you how, for instance, just give an example how this looks like. So I take this slightly more complex program, and I want to do as before in level 1, except that now I have this update on X, and I don't get a nice recurrence equation because I have a probabilistic update. Okay, so here I have this randomized distribution. So the probabilistic updates that we are encoding in the loop look like this. Okay, so both left and right hand side of the updates are some polynomial expressions, but depending which one you take, it depends on some probabilistic distribution Pi. So as a result, what we do, we compute instead of standard algebraic recurrences, we map the polynomial updates of the probabilistic loop into so-called stochastic recurrences over E variables, and an E variable is an expected value of a monomial. Simplistically saying, it's an expected value of a particular variable. And what we show that in case of solvable loops, you can always map the probabilistic updates that look like this into stochastic recurrences that look like this. And this is thanks to the fact that moments have this nice property. So we pretty much have rules how we can compute expected values of complicated expressions, and these are the main values that main rules that we are using. expected value of a constant is the constant itself. If you have a linear expression and you want to compute the expected moment, well, you just decompose it into the expected value of x plus c times the expected value of y. And now the problem comes when you have product. If you have two random variables that depend on each other, you cannot say the expected value of x times y is the expected value of x multiplied the expected value of y, because there are dependencies among the random variables. So while you might say that computing expected values of arbitrary program variables or monomials or expressions of a program variable is sufficient, it's actually necessary, because there will be cases where you have to reason about expected values of product of program variables, and you cannot decompose them unless they are independent. So let me just show how this goes. And I would like to recall the level 1 case. So if I would give you this very simple, very concrete recurrence equation, level 1 would solve it. This would be the geometric sequence. By solving, I mean it will compute with a closed form that the value of x at iteration n is 2 at the power n times the initial value. However, when you have a probabilistic updates, so here I have a uniform distribution, the question, what will be the closed form representation for this? And how we do it, we use the 3 rules that I showed you before: expected values of constants, expected values of linear combinations, and expected values of nonlinear combinations. Apply these 3 rules to decompose expected values of arbitrary polynomial or monomial relations among program variables. So if you want to compute the expected value of x, well, it is expected value of x plus the expected value of a uniform distribution. The expected value of a uniform distribution is 1/2, so it's constant. Now, if you do the expected value of x squared, so if you would go for the second order moment for x, then you cannot just say, again, that the expected value of x squared is expected value of x multiplied by itself, because they depend on each other. So you have to compute what is x squared, so square this relation and decompose it by the rules given previously. So we solve these stochastic recurrences by computing closed forms over E variables. And E variables are not just variables of the program, but they are monomials over the program variables. And to get very concrete, let's just look into this example. And this is the algorithm for solving probabilistic solvable loops. So I want to compute the second order moment of this variable S. So how you compute it? Well, this is the input. Check what is it depending on. And relation of, so S is x plus y, so the expected value of x squared is going to be the expected value of this x plus y squared expression. Again, you cannot just decompose it into the product of itself. You have to compute the square of x plus y. So that's what's happening here. Okay, so just standard math. What is the square of x plus y? Is x squared plus xy plus y squared. And then I use rules to decompose them, to split them up. Which means in order to compute the expected value of s squared, I need to compute the expected value of xy, x squared, and y squared. I cannot go beyond. So there is nothing further that you can do here, because x and y are actually, they might depend on each other, and x squared clearly depends on itself. So then it means in order to compute the expected value of x, we need to compute the expected values of x squared, xy, and y squared, so the respective E variables. And once you have those expressions, add them up and you have the expected value of s squared. So it's kind of like a recursive or an iterative process, but you're always going to terminate. But actually, we prove that you're always going to terminate. So let's just go further for one more step. Let's compute the expected value of x squared. We read off the update. So you know that the expected value of s squared is the expected value of the respective update squared. So again, you compute, you unfold. Within the expectation, you unfold the arithmetic expression. And then it's getting a bit more ugly, but the point is doable. as long as you make sure that you use the right rules from moment computability. So in order to compute the expected value of x squared, well, you have to compute the expected value of y squared as well as of x. No, the expected value of x squared, sorry, depends on the expected values of f and f squared. And then for expected value of s, you just cumulate all these expectations. And you go further. Now you might ask, is it going to terminate? Actually, it's going to terminate. The argument is such you have finitely many variables that you can always compose them finitely many times. It might be a finite time until you're terminating, but you're going to guarantee that you compute all the necessary expectations for all e variables. And now, before I go further, just what I want to, so yeah, it might be a bit misleading. You might think that here I'm going to work with a nonlinear recurrence equations. I'm actually not. So this x squared, I can just replace this x squared by a new variable. It's not like I'm squaring eagerly a linear recurrence. I'm going to compute the linear recurrence corresponding to the expectation of x squared. So the expectation of x squared, it's a standalone e variable. And I want to have that dependency between the expectation of x squared at the n+1 iteration in terms of the expectation of x squared at the nth iteration. And everything else corresponds to the C-finite case. So if you do this process, these are the things that you can compute. You can compute all the expected values which are necessary for this particular program in order to compute the second order moment of S. But again here, just like in the level 1 case, now we are in the probabilistic solvable case. Why is it solvable? Because what we do, we take level 1, which is the solvable polynomial case, polynomial non-deterministic case. And what we do, we extend this level by random polynomial assignment and finite value conditions so that we ensure that the resulting C-finite recurrences, so the resulting recurrences over expectation values yield you C-finite recurrences over E variables. So again, we can compute all the closed form solutions, but now we are computing closed form solutions over expectations. So the recipe remains the same. What we do symbolic summation as before in level 1 to compute closed forms. And we actually now do also moment-based computation by exploiting properties of higher order moments or statistical moments. And this approach can be further similar as before. You can use this approach towards probabilistic termination, so answering questions of almost or positively almost surely terminating loops. You can use it for sensitivity analysis, even for probabilistic inferences. But in both level 1 and level 2, the main crux of the approach was that the polynomial arithmetic, independent if it's probabilistic or non-probabilistic, is going to represent it by linear recurrences with constant coefficients, either over loop variables or over E variables or expectations. When this is not anymore the case. What happens when you start allowing a bit richer arithmetic? You're immediately hitting undecidability. And here's one such loop, which we cannot handle in the previous 2 levels. And the reason I don't show you the probabilistic setting, but this can also be generalized to the probabilistic setting. So if you are checking this loop, the issue with this loop is that we have polynomial updates. So if you look at the update of B, you have actually a nonlinear dependency on B itself. And that nonlinear dependency on B itself will not give you a C-finite recurrence. It will actually give you a so-called P-finite recurrence. So we destroy the nice properties of symbolic summation that we can do for program analysis. Because so it's only known that only C-finite recurrences always admit closed form solution. Nothing beyond it has this nice characterization. So we do allow richer arithmetic in the program, but by that, with these 2 updates, we actually have non-C-finite recurrences, which means there is no algorithm from symbolic summation that can be immediately applied. So whatever we did in level 1 for solving such or reason about such loops are going to fail here. Well, this, however, doesn't mean that we cannot do anything. We can do. try to come up with some program transformations by eliminating the sources of unsolvability. So unsolvability means that refers to those variables that destroy the C finite properties. And in this case, those variables, so the variables that make this loop unsolvable are A and B. Now the question, is there some linear or polynomial transformation? We don't want to go out of the polynomial domain. Is there some polynomial transformation among the variables that destroy solvability that if you use that transformation, you can go back to the solvability? Well, in this example, it's relatively easy to see. Sum them up. If you take the sum of the two variables that destroy solvability, so A and B, then you get the new sequence xn, and actually that satisfies a C finite recurrence. So which means I can work with some unsolvable loops. If I find a polynomial transformation among the loop variables that destroy solvability, such that the polynomial transformation may give me a C finite recurrence, then I can go back to level 1. I do the program variable transformation. I simplify this program into this program. And program that on level 1 we solved. This we know how to solve it. So we compute the invariance over x and y, which is this one. And by transforming back to the respective variables, you have the polynomial invariance for A and B. So in principle, what you can do by finding the right polynomial transformations among variables that destroy solvability, you can actually compute closed forms for loops whose variables do not have an analytic closed forms. You do not necessarily have to compute the closed forms of A and B, but it's enough to compute the sum of the closed forms of A and B. So we can do unsolvability. And we have this paper which is about solving unsolvable loops. So it's a quite conflicting title. But the point is that you can use whatever we had from level 1 or level 2, depending on whether it's probabilistic or non-probabilistic, in order to address non-C finite recurrences by finding polynomial relations among the variables of the loop that destroy solvability conditions. If you find those polynomial relations, and those polynomial relations are C finite expression, you actually can reduce the unsolvable loop into a solvable one. So it's a big if, and therefore we don't really have definite decidability. We have only kind of relative decidability, relative completeness. So if there is such a polynomial up to a particular degree, and this is nice because it's an enumerative search, then we find it for you, and then you can translate the polynomial, an unsolvable loop into a solvable one. So what happens here is really you track the dependencies of unsolvable and in particular unsolvable variables, or variables that give you the unsolvability, and do polynomial constraint solving by template analysis over the particular polynomial template that you're looking for. So with that, I'm kind of towards the end of the talk. So these are the 3 levels I wanted to discuss. And I mainly discussed in terms of invariant generation, but I highlighted applications of polynomial solvable loops or probabilistic solvable loops towards termination, sensitivity analysis, loop synthesis, and many more. And it's just like in a game. You have to go through various levels, and each level influences each other. So solving level 1 helps you in level 2 and helps further in level 3. But some of the level 3 problems can actually reduce to level 1, and you just reiterate the process. The main ingredients is that these loops, so we really view loops as recurrences, or in particular C finite recurrences, either over exact values or expectation values. We use polynomial, we actively try to stay in the polynomial domain. So if you start having exponential sequences, we abstract them away by polynomial relations, either over expectations or over higher order statistical moments. However, we always have to face the challenge of undecidability. It's very easy to be undecidable in the sense that you cannot compute the strongest polynomial invariant. And surprisingly, you might think, well, this is, who cares? Well, you might actually care, because it turns out that only very simple loops are solvable. So you don't have to have very complicated loops in order to be not solvable. This is maybe intuitive, but it's very easy. You can easily change. Affine loops are known to be solvable. P-solvable loops will allow you a bit of multiplication among program variables, and you still remain solvable. Extended with probabilistic choice, it's still prop solvable. But already if you just allow, and this is actually surprising, so there is a result by Joel Vaknin and his team that actually shows that if you allow arbitrary polynomial arithmetic in loops, the strongest polynomial invariant cannot be computed. So it exists, but it's not computable. That's fine. I mean, maybe it's not as surprising because like arbitrary polynomial arithmetic is very rich. So how you will capture it? But the point that we just showed recently, you don't even have to go to that rich domain. Already if you have arbitrary quadratic updates, so already just x squared in a completely arbitrary way, it will always give you undecidability. So the best results that you can hope are for affine loops. There's still a gap between affine loops and arbitrary quadratic loops. The question, okay, how far can you push decidability? So I actually think this is a loop itself. You know, you start from level 1, go up to level 3. When you're undecidable, try to come down to the level that you can solve. Try to push the boundary on decidability. Quadratic loops are undecidable, but there are some patterns of restricted multiplications of quadratic loops that will still give you the decidability result. When you have probabilistic updates, things become even harder. So there are many open questions in that domain. And with that, I would like to conclude. And yeah, I'm happy to take questions.
Yeah, thank you very much. Do I have a mic? Okay. Yeah, thank you very much. I'd like to open the floor for questions, discussion, please. Yeah, Masha.
So first of all, thank you so much for the talk. This is absolutely fascinating work. What I wanted to ask was, you rapidly move into unsolvable. And, you know, we kind of know that, and, you know, we're grateful that a bunch of things became more solvable than before. But now what? So what do we do in the world of automatic program reasoning now that we know that most loops are not decidable? Where do we go from here?
Yes, I think there are two ways to answer that question, or multiple ways to handle it. So I think we knew for a very long time that, I mean, we knew just from Turing that this is going to be a semi-decidable problem. And so there is a theoretical answer to your question, saying that it's actually good to know what can be expected, right? So if you want to generate polynomial invariants or strongest invariants for arbitrary polynomial loops, don't even hope for it. Okay? That said, you can actually restrict further in practice. So maybe you don't want to work over arbitrary fields, but you're only interested into polynomials, let's say, over finite domains. Then things can become more solvable. Another thing can be, so what happens if you start getting loop conditions? Because here I actually want to compute always the strongest polynomial invariant. I don't even care what the loop conditions are. But sometimes you can have loop conditions taken into account. That will mess up solvability immediately, but it actually, again, brings you back to the level 1 question. Okay, are there some classes for which you can come up with a completely automated approach? And finally, I mean, I don't think, and also the very first slide of the talk was this big screenshot. So it's unrealistic to use these methods for immediately on a code of 200,000 lines of code. So therefore, we need the others. We need symbolic execution, we need testing, we need trace evaluation, many other techniques. And then only when you identify the hardest parts, which might be unsolvable, you don't know yet, then try to use loop analysis based on recurrence equations.
Any other question? Yeah. I think it's Andre.
Yeah. Why are
preconditions easier than postconditions for loops?
I don't think they are easier. Well, I'm not sure, because you can do very similar. You can reverse engineer completely what we have here. So I can start with a post condition and try to generate you a polynomial invariant. And I want to generate a loop satisfying that invariant. So I kind of giving the preconditions on the necessary requirements for the loop for which the post condition should satisfy. So I'm not sure what you're saying, why they are easier. Okay. I don't see why, because the preconditions are just as polynomial as the post conditions. So they, like generally handling polynomial preconditions, it's as hard as generally handling polynomial post conditions.
Just one final question. Yeah, Martin.
Yeah. So we didn't do it for vampire, but we had some like case studies, and surprisingly, you don't have more than affine loops. You rarely go beyond the affine loops, and it also kind of gives you the intuition that programmers would also not write very complicated programs. So in practice, also when you go in the, for instance, the svcomp repository or other repositories, it's very hard to find these very complex loops, like meaningless loops in applications with polynomial arithmetic. It's mainly you would stay in affine, and what you could have, what we also saw, and this is why we extended the solvability criteria, you might have restricted multiplication about loop counter and some variables. But you would never go of polynomial, rarely go, let's say on the deterministic case for arbitrary polynomial arithmetic.
Okay, that brings me to the end of this session. I would like to thank Laura very much for the great talk.
Thank you very much.
For being here.